We have some more vector questions. This question is on velocity. So distinguish between speed and velocity. So like distance and displacement, the key difference is that speed is a scalar. It only has a magnitude, right, an amount, whereas velocity is a vector, meaning it has an amount and a direction. So speed is a scalar, meaning it only has a magnitude, whereas velocity is a vector, meaning it has both a magnitude and a direction. Right, so for example, speed is you are driving 100 kilometers per hour on the motorway. Whereas velocity would be you are driving 100 kilometers per hour on the motorway exactly north. Right, so if you specified a direction. Alright, and part B, draw a velocity vector to represent an object moving 20 meters per second, so there's our magnitude, 45 degrees north of east, and there's our direction. Right, so let's represent that on a vector diagram. So to draw a vector, we know it has magnitude and direction, so the magnitude is given by the length of the vector, and we can of course label it. So in this case the magnitude was 20 meters per second. Yeah. Compared to a vector, let's say, of 10 meters per second, when it has a lower magnitude, the length of the arrow is less. And now what about the direction? So it says 45 degrees north of east. So there's a lot of different ways to specify a direction. One of the most common is with an angle. However, we need to know where we are measuring that angle from. So in case you forget your cardinal directions, north, east, south, west, and it said 45 degrees north of east. So starting at east, we go towards north by 45 degrees. Like so. So that blue line is the horizontal, which is in line with east, and we're going 45 degrees north of that. In other words, we're going anti-clockwise by 45 degrees. So this would be our vector diagram. Another way of describing this angle would be 45 degrees anti-clockwise from the horizontal. Right? There's a few ways you could describe this angle, but the best is with a diagram, which is why that was our first step, to draw the vector diagram. And then the next question, eraser, come back, come on. Next question is calculate the horizontal and vertical components of the vector in part B. So looking at our vector diagram, the dashed blue line is the horizontal direction, and this dashed black line is the vertical direction. So to make up this vector, we need part of it to align with the horizontal and part of it to align with the vertical. In other words, we're splitting up this vector into two directions, which makes calculations, for example in kinematics, a lot easier when you can deal with one dimension at a time. So in this case, we're looking for a horizontal vector and a vertical vector. Well, let's use a different color. So how do we calculate those vectors? Well, what's their directions? Well, horizontal means it's aligned with east, and vertical means it's aligned with north. So we actually already know their directions because we're trying to find vectors in specific directions. So that's halfway done. The next part is to find their magnitudes, and you'll notice in drawing this red and light blue arrow, we've formed a right angle triangle, right, where the red and light blue arrow meet, 90 degrees. And so we can use our SOHCAHTOA with the hypotenuse given and one of the angles to work out the lengths, which are actually the magnitudes, right, because the length of a vector is its magnitude, the lengths of these vectors. So let's work out the vertical component first. Looking from the angle, we're looking for the opposite, and we are given the hypotenuse, so we will use the sine ratio. So sine of the angle is equal to opposite, right, in this case that's what we're looking for, divided by the hypotenuse, 20. So rearranging that, we get the vertical component, so Vy, V subscript y, is equal to 20 sine 45. And so we can compute that on our calculator. 20 times sine of 45 degrees, giving us 14.14 meters per second. And rounded to one significant figure, because the hypotenuse velocity is also one significant figure, would be 10 meters per second. So that's for the vertical direction, right, following that light blue arrow. For the horizontal direction, well, we know the direction is to the right, right, along east. Similarly, we can work out, let's denote it Vx, x being the horizontal, as we're looking for the adjacent. We have the hypotenuse, so we'll use the cosine ratio. So cosine of the angle is equal to adjacent, the horizontal component of velocity, divided by the hypotenuse. So rearranging for Vx, we get 20 cos 45. And if you know your trig ratios, you know that sine 45 and cos 45 are actually equal. So Vx should equal 14.14, or 10 meters per second to 1 SF as well. And so have we answered the question? Have we found the horizontal and vertical components? So a reminder, these are vectors, so we need a magnitude, both are 10, and a direction, which I've shown by the light blue and red arrows. Right, but we could also say 10 meters per second up and 10 meters per second to the right, just to be extra clear. And so this skill is an achieved skill that's used in kinematics problems to split up like initial velocities into each direction, so you can then use your kinematics equations to solve for other unknowns. Alright, on to baseball. So you pitch a baseball at 40 meters per second to the right, so that's a velocity, magnitude, and direction. The batter hits it back to the left at 20 meters per second, again another velocity. Calculate the change in velocity, including the direction. So 40 meters per second to the right, and then the batter returns it at 20 meters per second to the left. So change in velocity, delta V, is the final velocity minus the initial velocity. final minus initial. So wherever you see change in something, like change in distance, it's the final distance minus the initial. Or change in time, final time minus initial. Same for velocity. Now, the final velocity was after the batter hit it, so it's 20 meters per second to the left, whereas the initial velocity of the ball was when you pitched it 40 meters per second to the right. Now, when finding differences of vectors, it's very important to be mindful of the sign. So let's define which way is positive and which way is negative. So I will define to the right as positive. So the final velocity is 20 meters per second to the left, which means the value would be negative 20. Right, where that negative just tells us that it's moving to the left. And we take away the initial velocity, which is 40 meters per second to the right, so that will remain, VI will remain positive, and we're subtracting that. So we'll end up with negative 20 minus positive 40, giving us minus 60 meters per second. Now, is that a vector? Yeah, it is. We have the magnitude, which is 60, and the minus tells us that it's going, or the change in velocity is to the left. So let's think about that for a second. The change in velocity is 60 meters per second to the left. So after you pitched it at 40 meters per second, the batter would need to stop the ball, right? In other words, give it 40 meters per second to the left, and add on top of that how fast it came back to you at 20 meters per second. So that one checks out. And that would be our final answer. Because we've defined the direction with the sign, you could also write 60 meters per second to the left. Alright, next up. So back to baseball. This time though, same pitch speed, 40 meters per second to the right, but the batter, it skims the top and hits it directly upwards at 30 meters per second. Calculate the change in velocity, including the direction. So this time, 40 meters per second to the right, and then the batter hits it 30 meters per second up. Cool, so we have initial and final velocity. Now what's different about this problem compared to part D is that we are no longer in one dimension, we are now in 2 dimensions. The same rules still apply. We will define which way is positive. So like before, I'm going to have to the right as positive, but I'm also going to have up as positive. Right, because we have 2 dimensions. We know the change in velocity is the final minus initial. However, to add vectors in 2 different directions, we can't just do, for example, 30 minus 40. Alright, that's a good first guess. So like part D, we're just substituting in the magnitudes, but for 2 dimensions, that's not quite right. Instead, when we subtract a vector, it is the same as adding the vector, but by flipping its direction. So VF being 30 meters per second upwards, if we are subtracting 40 meters per second to the right, so these are vectors, it is the same as adding 40 meters per second to the left. Right, this is called vector addition, and we can change the sign by flipping the direction of the arrow. Now, to add vectors, we know that we join them head to tail and find the resultant vector. So just labeling that 30 and 40. In this case, now it's 40 to the left, and that's because we're adding it instead of subtracting it. So adding these two vectors on a diagram, we draw head to tail, like so. And the result of that would be tail of the first vector to head of the second. So that green arrow is our velocity, our change in velocity, delta V. And we know to find the magnitude, we have a right angled triangle. So the magnitude of delta V is each side squared and then all square rooted. So 30 squared plus 40 squared, shift square root, shift answer to give 50. I should have got that. That's a 3-4-5 triangle, right? 50 meters per second. That is its magnitude. However, we need to specify the direction. So looking at this diagram and thinking of the context, it's pretty clear that for the batter to remove all of this velocity that's to the right, a big portion of it must be to the left. So that's the 40 to the left, as well as it adds 30 meters per second upwards, right? 30 meters per second upwards. So the direction is northwest-ish, but we need to be more specific than that. So we could calculate this angle right here, label that as theta, and we know from that angle, we know the opposite side and the adjacent side. We also worked out the hypotenuse, but let's use the opposite and adjacent. So we will use the trig ratio tan of the angle is equal to opposite divided by adjacent. So the angle is inverse tan of that ratio, 30 over 40. Checking on our calculator, making sure that we are in degrees, not radians. 30 divided by 40 gives 36.87 degrees. And so how would we formulate our final answer? Well, we have a magnitude and we have an angle. So let's put it into a sentence. The change in velocity, denoted by delta V, will be 50 meters per second at an angle of 36.87 degrees. Now, what are we measuring that angle from? Well, from our diagram it's clear, but in words we would say at an angle of 36.87 degrees clockwise from the horizontal. Cool. And that's just being very clear with our magnitude and direction. But if you stopped here, I mean, with your diagram, that's still very clear. So just to recap D and E, in one dimension, it's enough to define our positive direction, and then when we subtract, making sure we replace the magnitude with negative. For example, the final velocity, since it was to the left, we replaced it with negative 20. And the final answer, the sign, will tell us the direction. However, in 2 dimensions, I recommend you do this first line here, the symbolic vector addition. So that's this line here, so that when we subtract, we know to flip the direction. So when subtracting a vector, we can add the opposite direction. And why we do that is because we know how to do vector addition, right? We find the hypotenuse using Pythagoras' theorem, and then we can find the angle using our trig ratios. All right, onwards. Question F. So you and your best friend, who you haven't seen in 5 years, run to each other to hug. Oh, so cute. Now they run towards you at 3 meters per second, but you're not as excited to see them, so you only run towards them at 2 meters per second. Draw this scenario using two velocity vectors and calculate their velocity relative to you. So you're going at 2 and they're going at 3. And notice how I drew their vector of 3 meters per second a bit longer, right, to indicate the magnitude. Now, their velocity relative to you. So let's have a think. So you're going towards them at 2 meters per second. They're coming towards you at 3 meters per second. So it'll appear like they're moving towards you at 5 meters per second. So as an equation, their velocity relative to you, so velocity of friend relative to you would be their velocity taking away your velocity. Right? And if we define to the right as positive, we have your friend's velocity, so 3 to the left, meaning it would be -3, taking away your velocity, which is to the right, so that will be +2, giving -5 meters per second. So the velocity of your friend relative to you is 5 meters per second to the left. And so that's in one dimension. Very similar to question D, right? Finding the change in velocity. Just being careful we define which way is positive, and relative of our friend's velocity relative to us is their speed minus our speed. And so the next one is, okay, you and another motorist are approaching a four-way intersection. They are traveling 10 meters per second north, and you are traveling 8 meters per second east. Calculate their velocity relative to you. So, they're going 10 meters per second north, and you are 8 meters per second east. Oh, let's draw those to scale. So that will be a smaller vector. And what question is this? This is G. Okay, so you're both approaching the intersection. But like part F, to find their velocity relative to you. So let's just reread the question. Yeah, their velocity relative to you. So the car relative to your velocity would be the car's velocity take away your velocity. And now we don't have one dimension here, but we will still define which way is positive. And in this case we have 2 dimensions, so I'll define right as positive and up as positive. So like before, when we were calculating change in velocity, when we subtract a vector, it's the same as adding the vector in the opposite direction. Right, so I'll just draw this out with symbols. So velocity of the car was 10 meters per second upwards, and we're taking away your velocity of 8 meters per second to the right. That is equivalently 10 meters per second up plus 8 meters per second to the left. Alright, so we turned that subtraction into an addition by flipping the direction of your velocity vector. And so with that, we know how to perform vector addition. So let's draw our vector diagram. So 10 meters per second upwards and 8 meters per second to the left. The addition of these two vectors will give the resultant vector, right, connecting the tail of your velocity to the head of their velocity. And we can work out this magnitude, and then we can work out the angle to specify the direction. So working out the magnitude, we know by Pythagoras' theorem, the sum of the square of the sides, square rooted, will give the magnitude. So what's that? 64 plus 100, square root of 164, square root 164 gives 12.8 meters per second. And now to work out the angle, we will use our trig ratio, tan theta equals opposite. So from the angle, we know the opposite divided by the adjacent. And so the angle would be the tan inverse of that ratio. So shift tan, making sure we are in degrees, 10 divided by 8, 10.54 degrees. And so the velocity of the car relative to us, velocity of car, or relative to you, would be 12.8, or to one significant figure, because the other velocities are given to one significant figure, would be 10 meters per second. And then at an angle of 10 to one sig fig, what would that be? Yeah, 10 degrees. 10 degrees, and now how would we describe that? We would say clockwise from the horizontal. Yep, and again, that bottom sentence is just putting it in very clear words. However, this diagram plus these two calculations are sufficient, right? Because that is still very clear. And then I think that's it. Yep. Awesome. I'm going to go eat my lunch. Bye.